This question is related to synchronous motor. Now let us see the question. The damping winding in a synchronous motor is generally used to prevent hunting and provide the starting torque. Now we see what is meant by hunting. Hunting means if there is sudden change in load, the rotor starts oscillating about its new position of equilibrium corresponding to the new load. This oscillatory motion is called hunting. How it is prevented by the damping winding? The oscillatory motion of the rotor sets up eddy currents in the damping winding which flow in such a way as to suppress these oscillations. In this way, the damping winding prevents hunting. This question is related to DC series motor. Let us see the question. For a DC series motor with a saturated condition of the field circuit, the torque developed is proportional to armature current IA. We know that torque proportional to pi into Ia. For DC series motor, pi proportional to Ia, therefore torque proportional to Ia square. After saturation, pi becomes constant, so torque proportional to Ia only. In this graph, we see before magnetic saturation, the shape of the curve is parabola because torque is proportional to Ia square. After saturation, it becomes straight line because torque proportional to Ia only. DC series motors are best suited for traction because torque is proportional to the square of the armature current and speed is inversely proportional to the torque. If torque is proportional to the square of the armature current, the motor develops high torque, required torque when the load is increased. If speed is inversely proportional to the torque, the motor develops high torque at low speeds and low torque at high speeds. These are the basic requirements of the traction. A delta to star transformer has a phase-to-phase voltage transformation ratio of A is to 1. The line-to-line voltage ratio in star to delta is given by. They are given delta to star transformation ratio that is equal to A by 1. They are asked line to line voltage ratio in star to delta connection. We know that in delta connection phase voltage is equal to line voltage. In star connection phase voltage is equal to line voltage by root 3. The given ratio is phase voltage in delta by phase voltage in star is equal to A by 1. Substitute phase voltage in delta connection is equal to VLD. Yeah, similarly, we substitute phase voltage in star connection is equal to VLS by root 3. From this equation, we get line voltage in star connection by line voltage in delta connection is equal to root 3 by A. This is the answer. The speed control of the DC shunt motor in both directions can be obtained by Ward-Leonard method. This figure shows Ward-Leonard system of speed control. This method gives wide speed control from a maximum in one direction through 0 to the maximum in the opposite direction. The residual magnetism of a self-excited DC generator is lost. To build up its EMF again, what will we do? The answer is field winding must be excited by a low voltage DC supply. The important points we have to know are the first one is what is residual magnetism. The residual magnetism is the small magnetic field left in the iron cores of the shunt fields when the generator is at rest. The second one is what is the purpose of residual magnetism. It is necessary to build up its EMF of DC generator. The third one is what will happen if the residual magnetism is lost. If the residual magnetism is lost, the generator will not produce any power at the startup. This question is related to DC shunt motor. Let us solve this problem. A 50 kilowatt 200 volt DC shunt motor has armature resistance of 1 ohm and shunt field resistance of 100 ohm. At no load, the motor draws 6 ampere from 200 volt supply and runs at 1000 rpm. What is the total copper loss of the machine? In this problem, they are given armature resistance Ra is equal to 1 ohm, shunt field resistance RSH is equal to 100 ohm, and no load current I0 is equal to 6 ampere. Total supply voltage V is equal to 200 volt. What they are asked total copper loss of the machine. In this problem, they are given no load current only, so we find total copper loss of the machine at no load only. So, how can you find total copper loss? Total copper loss at no load is equal to armature copper loss at no load plus shunt field copper loss at no load. First, we find no load armature current IA naught. IA naught is equal to I naught minus ISH. Substitute I naught and ISH, we get IA naught is equal to 4 ampere. Then we find ISH is equal to V divided by RSH. Substitute V and RSH, we get ISH is equal to 2 amps. Then we find total copper loss at no load by substituting armature copper loss at no load plus shunt field copper loss at no load. We get total copper loss is equal to 416 watt. Why is the armature core of a DC machine laminated? The answer is to reduce eddy current loss. How is the eddy current loss reduced? By using laminations, the path of eddy currents is divided into several small loops and hence area of the eddy current loops is minimized. We know that resistance of the lamination is indirectly proportional to the area of the loops. If the area of the loop is reduced, the resistance of the lamination is increased. So the sum of the eddy currents in the laminated core is smaller than the current in the solid core. Another point we note that is eddy current loss is directly proportional to square of the thickness of the lamination. In order to reduce eddy current loss, the thickness of the lamination should be kept as small as possible. For a people machine, the relation between electrical and mechanical degree is, the answer is theta electrical degree is equal to P by 2 into theta mechanical degree. Why? Because for a people machine, P by 2 cycle of EMF will be generated in one revolution of rotor. 100 kVA, 1100 by 220 volt, 50 Hz single phase transformer with 2000 turns on high voltage side. The open circuit test result gives 220 volt, 91 amps, 5 kilowatt on low voltage side. The core component of current is approximately. They are asked the core component of current. We know the formula of core component of current is equal to I naught cos pi naught. They give I naught value is 91 amps. Then we need only cos pi naught. We can calculate cos pi naught from P naught. Substitute P naught, V naught, I naught, we get cos pi naught. And substitute cos pi naught and I naught, we get the core component of current is equal to 22.72 amps. This question is asked in 2018 competitive exam. It is related to induction machine. Let us see the question. What can be obtained by equivalent circuit of an induction machine? The answer is complete performance characteristics of the machine. This circuit represents the equivalent circuit of the induction machine. The data obtained from the machine, we can calculate efficiency, torque, losses, rotor output, etc. This problem is related to transformer. Let us solve this problem. A 25 kVA 3300 by 230 volt single phase transformer has iron and copper losses of 350 watt and 400 watt. The efficiency at 0.8 power factor is. In this problem, they have given rating of the transformer is 25 kVA, primary voltage is 3300 volt, and secondary voltage is 230 volt, and iron loss is 350 watt and copper loss is 400 watt. What they asked the efficiency of the transformer at 0.8 power factor. We know the formula of efficiency, heater is equal to output by input. Substitute input as output plus losses. Losses consist of copper loss plus iron loss. Substitute efficiency in terms of full load kVA is equal to x into full load kVA into power factor divided by x full load kVA into power factor plus x square copper loss plus iron loss, where x is load of the transformer. That is x is equal to 1 for full load, x is equal to half for a half load, x is equal to 1 by 4 for water load, like that. So here they didn't mention x value, so we take x as 1. Substitute x is equal to 1 and full load kVA is 25,000 and power factor is zero point 0.8. Copper loss is 400 and iron loss is 350. We get efficiency is equal to 96.39 percentage.